everybody. Welcome back. Hope you had a nice break. So we're going to pick up where we left off. So if you could open that EE 101 Python collab again, then we'll get started. So before the break, we were talking about single images. Well, now we're going to move and talk about a collection of images. And we're going to look at, instead of the digital elevation model we were looking at before, now we're going to transition and start looking at Landsat data. So the first thing we're going to do is we're going to get that Landsat 8 data. And the goal for this mini part is we're going to look at the Landsat data and find the cloudiest image and the clearest image around the Geo for Good event venue here in Mountain View. So I've loaded that Landsat 8 data. Now I'm going to create the geometry. So this is the location for the Geo for Good Event Center. I am going to define the visualization parameters. These are the default visualization parameters for viewing Landsat in RGB. So as I'm sure you can imagine, like Landsat data, there's a lot of images, right, in the collection. So we need to filter. First, we're going to filter by space. So we're going to only get images that contain this event center. And then we're going to filter by time, because we don't want to look at, it just makes it a more efficient computation. So we picked the year 2016. This is very arbitrary. And then once we filtered it, so we filtered by space, by time, and now we're going to filter by this cloud cover property. So we can use this cloud cover property to find the least cloudy image, and then we can also sort it in the opposite order and find the most cloudy image in that collection. And then we're just going to display those two images. Before we were using a H-box, which allows you to display images or maps side by side, H for horizontal, and now we're going to use the V-box. So we're going to display the most cloudy on top and the least cloudy on the bottom. What do you guys think? Do you think Mountain View is cloudy? It's honestly it can be pretty cloudy in the morning. Let's take a look. Wow. So there is the most cloudy and the least cloudy. So now we're going to move on and talk about composites and mosaics. So for composites, often we don't want the cloudy image, and so like we don't want, and we also don't want like shadows in the image. So composites look at all the images in a single area, and they aggregate the pixel values over all of those images. And it's common to use the median to help remove the effects of cloud cover and shadows, because cloud cover pixels are very bright and shadows are very dark, so taking the median allows you to get a clearer image. So that's what composites are. And mosaics, when I first learned this, I was like, oh yeah, I remember being like a kid and doing arts and crafts and making a mosaic. Well, that's kind of what we're doing here. We're taking images and kind of stitching them together side by side. That's enough about me talking. Let's see what it looks like. So first, we're going to, again, we're looking at the Landsat data for the year 2016, and it's centered around this Geo for Good venue. And then we're taking the mosaic here, and then we're taking the composite here, the median composite. So then we're going to display them side by side. So the one on the left is what is it, guys? Is it the mosaic or the composite? Putting everyone on the spot. So it actually is kind of hard to tell, because I can see lines here which makes me think it's the mosaic, but the one on the left is the mosaic. And like when I first saw this, I was kind of confused. I was like, wow, like that's a big line, you know? And it turns out it's because of the Landsat orbit, and I'll show that to you in a second. But I also want to talk briefly about the composite. So on the composite side, there's not those sharp lines because, again, it looks at each pixel and it takes the median pixel. So if there was a sharp line, that line would get kind of muted out because it wouldn't take the brightest value. It would take the median. But let's look at the Landsat orbit to understand why there is this white line. How many of you have seen the Landsat orbit? So not everybody. It's pretty cool. I thought it was really cool. Maybe I can. So it goes in, it kind of reminds me of those chocolate oranges. I don't know about you guys. But yeah, you can see in a minute, it's going to make its second pass. So they're not exactly overlapping all the time, and that's kind of why we have this white line in the mosaic. I thought this was really cool. So we talked about composites and mosaicing. Another common operation is masking. So imagine you only want to hide certain pixels from the user. For example, maybe we only want to see the land data, and we don't want the water data anymore image. That's what we're going to do here. That's masking. Masking makes the pixel values transparent and not render them. So in order to create a mask, we're going to use a trick. So there's this Hansen Global Forest Change dataset, and in this dataset, there's a column with it's called the data mask column, and in that column, it has a value of 2 for water, a value for 1 for land, and 0, a value of 0 for no data. So we can use this dataset just to make a mask. We know that if the pixel value has a data mask of 1, we want to keep it, like show it, because we want to show land. And if it has anything else, we don't want to show it. So what we do is we load the global forest change dataset. We select that column that has the information about the mask. And then we say, okay, the mask we want is when this column's pixel value is 1. So then we can apply that mask we just created to our Landsat data. So that's what we're doing right here. The median is the median composite that we just created for the Landsat data from before, and we're going to apply the mask to it. So that means it looks at the pixel value for Landsat, and then it also, for that pixel value, looks and sees if that data mask value is 1, and if it is, it'll show it to us. If it's not, it will hide it. And then I'm just going to show you what it looks like. So as you can see, we now have watercolor water instead of satellite water. Does anyone have any questions?
For all data sets that you sort of want to do this for?
Yeah, you could. Yeah.
Okay.
It's pretty fun. I mean, it's not related. Like the forest change data set isn't related to Landsat, but well, maybe it is. But like it is probably. Okay, I don't want to speak to that. But like, sorry. But like, they don't have to be related. You could apply it to whatever. Yes, Kel?
What happens if you have a mask that's a different resolution than the mask that you're trying, or the image that you're trying to update?
Tyler? I don't know.
It can be confusing around the edges, but in general, you can mix and match masks that are in different projections and get them to work. You may have to, what's known as reproject or apply a different projection to an image before you're combining them, but in general, I think it works fine. Have you seen it not work fine? I guess that's the question.
That was a seed question.
Ah, okay.
Thank you.
There's always quirks that we learn about, though.
All right. I'm going to pass it off to Tyler to talk about the normalized difference vegetation index.
All right. Thank you. Yeah, one thing I did want to point out that I really like about not just the Landsat orbit, but the ability to just put rich things inside of your notebooks that can provide additional description. Imagine trying to describe that in a code comment or something, like how the Landsat orbit is. It's really valuable to be able to do all this rich markup within a notebook. All right, we're gonna go down to this section now, the NDVI mapping a function over collection quality mosaic. We have been building up to this, basically describing images, describing collections, and how you can start manipulating them. But that's, if you're just doing up to this point, you really wouldn't need Earth Engine. You're not really like harnessing the full potential of it. But in this section, we're gonna start doing more of processing large image collections, which is something that Earth Engine excels at. But first, gonna give a little bit of an introduction into what we are going to calculate. It's a vegetation index. If you've taken a remote sensing class ever, you've probably seen NDVI, because that seems to be the hello world of remote sensing analysis. But it basically is taking two spectral bands, the red band, the near infrared band that we have here, and doing a ratio of the difference over the sum of them. That's what NDVI is. It's, there's a whole series of indices that are kind of have this form, but this is one of the ones that we use most often for, because it's relatable to people that have seen, some slightly dead vegetation versus really vigorous live vegetation. It looks to you visibly, you can tell that when it's getting into the fall, the visible light, you're going to get a lot more of a red coming off of it, the reflection of the red. And what isn't apparent to our own eyes is that the near infrared is going to be reduced in that situation when they're getting into that phase of their cycle. But the ratio between these two will give you the value of NDVI. And in this example, we have a high value of NDVI for this green plant over on that side, and this one that is kind of getting towards the end of its season has a very low NDVI. It's still above 0, but it's a lower positive value. There's a lot of links in here that if you really want to study more about why people think these vegetation indices are useful, they're there. But let's get into how we can calculate this in Earth Engine. So to start off with, we're going to isolate a single image from our Landsat collection. So the code up here is taking Landsat H, which we defined much earlier in this notebook, which is the image collection of Landsat 8, and we're going to filter it by a particular point that is defined here, and then also filter it by a date range, 2016, sort it by cloud cover, and then takes the first image, which should give us the least cloudy image in that stack. And we're going to use that to kind of show off this algorithm, like work on a particular single image before we move up to a larger image. Now the equation for NDVI that we went over earlier can be implemented in Earth Engine as follows. We take that image that we're working on, select band 5, select a single band there, and then the next line is going to define the red image band objects called red, and then we have this really wordy, verbose way of subtracting and dividing appropriately, that we're going to take the near infrared, subtract off the red, and then divide that by this sum, basically, of near infrared plus red, and then finally rename it to something that we will understand, NDVI. So the next one down here is going to define visualization parameters for what we calculated and then display it on the map. In this palette that we're using right here, it's defined from -1 to 1, which is the range of these vegetation index or the normalized difference indices. And the palette is going to be blue when it's negative, white, so over here is going to be a negative NDVI value, white when it's about 0, and then it goes up to green when it's a high value of NDVI. And this is for, you don't see any clouds or kind of strange things in here because we did that sorting of the images. Because this is so common in remote sensing to do these band ratios and calculate them in this way, we have a way to do it in a shorter way, a shortcut. There is a method called normalized difference that can be applied to an image, which will just basically do that difference and normalization by the sum. In order to demonstrate that, we're going to take our map and remove a layer. So this is kind of a new method that we haven't seen yet that the map can do. It can basically take a layer and remove it off. And then we will calculate NDVI again using the normalized difference method, passing in band 5 and band 4, and then finally add it back as a layer. So you ideally will not see anything change other than the layer disappearing, and then this shorter piece of code that we have here adding or calculating the NDVI object similarly and it being added back up to the map. All right, that's NDVI verbosely in Earth Engine. But now we have a way to show that we can do it on a single image. The next step in order to make it more useful in Earth Engine is to package that up in a function. And in Python, the way you define a function is by this def, D-E-F kind of modifier. Then the name of the function, which we're going to call add_NDVI. This function is going to accept an image that we pass to it, calculate the normalized difference, save that as an NDVI variable, and then add that as a band back on the original image to return it. So we're going to take a Landsat image that's passed in, calculate NDVI, append it to the end, and the function will return it back. So I'll run the definition here. So we have our function defined, and then I will try applying it to a single image right there. So we're passing our image to the add NDVI function. And then finally, I will take the result that came back out, which is called, there we go. This got a little confusing. I'm using NDVI all over the place, but my image object is called NDVI there, and I'm going to add that to the map. And so this should look identical to what we did before. The difference is we are now using a function to calculate NDVI, but this function could be a much more complex example as well. In this case, it's just really simple. But the real power of having a function is now that we can use a simple command that's just called map, and we have to apologize always for using map in so many different ways when we're doing geospatial stuff. In this case, it's the mathematical map operation that takes something, in this case it's a function, and it applies it to all elements in a collection. So we are going to map this function add NDVI over all of the images in the image collection. And that's what that simple line does, but it's rather powerful in kind of the implications because we have now moved away from working with a single image to working with potentially a really large image collection. And then finally, I'm going to add that data that we calculated back onto an interactive map. One thing that is different than if you were doing this in the code editor, when you're adding an image collection to the map in the code editor, you can add an image collection directly, and it will take the mosaic underneath the hood. In this case, I actually had to call mosaic because I haven't coded it up yet to how to handle image collections. But that will come in the future. We'll get rid of that. But we took the mosaic of that entire stack with NDVI images in a collection, added it to the map, and if I zoom out, then you'll start seeing that it's not just that one image that we were calculating, but there should, as you wait long enough, the tiles will keep filling in wherever there is data available. Unless the Earth Engine servers want to sleep, then we might not see that going. Zoom in a little bit. Sometimes I find I have to zoom in and out a little bit to get it to like wake up. But that is actually more the mapping library here rather than Earth Engine behind the scenes. Maybe I was asking it to do too much today. You can see that it's farther than one image. It just hasn't populated them all at this point within here. You can see like individual Landsat scenes are about this size, and we're calculating a lot of them at this point. So that is mapping a algorithm or a function basically that we've defined in Python over a collection. All right, any questions on that before I go to the next? Yes. We'll wait for the, I got to get better at pausing and waiting so we can record it.
Thank you. And so, you know, obviously, because we did this over the whole Landsat collection, we didn't filter out cloudy images, which is why we're seeing all these streaks.
Yep.
So if we wanted to, we would just do the same kind of filter the image collection for maybe like some kind of cloudiness level if we
Yes.
wanted to. Okay, yeah.
Yep, so there's different places where you could insert that in. I would probably filter before you're applying the images just to save, but sometimes you want to calculate a value on the image and then decide whether to filter it out or not. But in that case, a lot more computation has to go on. But yes, you definitely can do that with your collection. Filter it down.
Hey there. You showed us a very nice verbose way of doing NDVI, which is fantastic. Can we also use our Python operators like plus, minus, divide signs, or is that like a no-go scenario?
Not this month. That has been one of my pet peeves with using the library. It's like I want to use the expressions, the operators that I'm used to in Python and use operator overloading so it behaves properly. So I'm going to talk a little bit about the library that I'm creating towards the end of this, but not yet, but that's something I really want to add basically to the library. Yep. Kel.
Is it worth mentioning expressions?
Expressions are a shortcut to be able to do something like NDVI in a string expression. I would just encourage you to look into the documentation if you're curious about that. I would say that's a intermediate before you get into like using the full Python operators, image expressions. They are useful in some cases. So ee.image.expression is where you would find that in the docs. All right, we're going to go to the next example here, which is another type of compositing, but instead of just stacking them up and ordering them and taking the median or the min or the medium, we're going to do something that's called a quality mosaic, is that we are going to take a particular property, or a band in this case, and use that to determine the ordering of the images. And this way we can, well, actually it'll make more sense as we're going through it here, but we can define a band. In this case, we've already calculated one called NDVI because we have applied our function towards all the images in the collection. And we can use that calculated NDVI value as the ordering for the collection before we take the mosaic on there. So in this case, it's going to preferentially take the image pixels that have the highest NDVI value. So even if you're using band 3 or band 12 or some other band that didn't go into the calculation of NDVI, that image will still be selected with all of its accompanying bands because that image has that pixel has the highest NDVI at that point. I'm going to show the result, and then we can talk, whoops, I didn't on the preceding slide or cell. All right, so what I just did, and I probably did this earlier but didn't mention it, is that I ran the cells out of order, which you can do, and is great to do in exploratory data analysis, but it can get very confusing for somebody that comes along later and tries to recreate what you did. So I think that's fine as we're like figuring it out, but every once in a while you probably want to stop and rerun everything from the beginning to make sure that all the cells were run in order.
You can show that too if you want
Yep.
to show the runtime, run all or whatever.
Yeah, there are, I'll show you in the menu. I'm not going to do that right
Yeah,
now.
just mean to show, yeah.
But there are all kinds of different options under the runtime menu that can say, hey, run everything before, or run them all, or run everything after. So you have a lot of choice of like which cells are being run. And so what I often will do is I'll restart and run all. That will still keep me authenticated, but it will run all the cells starting at the beginning after it clears the output. And that's a really good idea before you save and share your notebook. Do that first. Make sure it all runs still. All right, but in this case, I'm mapping out this quality mosaic, and it is displaying the RGB values of the pixels, so you get a true color looking representation, but the pixels that it chose, like which image did the pixel come from, is based on the NDVI value. So in this case, you'll get, in this case, it looks kind of like a dark true color representation of a cloud-free mosaic because we have done that ordering. It looks good over land. It looks really funny wherever there is water because water can, well, it's just basically the ordering of the NDVI values over water. The clouds are going to have a higher NDVI than the water pixels itself. So it's going to look usually pretty bright if you do a long time series of NDVI over water. But you could go back and use the masking technique that Kayla showed earlier to basically make that look more like water if you cared about that in your visualization. All right, so that is how you can create a greenest pixel composite. Any questions on that? All right, how are we doing on time?
We're good.
We got about a half hour left. Yep. All right, the next section is going to break away a little bit from the mapping and just show a few examples of how to do charting in a notebook with Earth Engine. And so this one is pretty, well, there's lots of different choices. So I'm going to show you one flow of how to extract data out of Earth Engine and pass it into a Python library. So we're going to start off with something that should look fairly familiar. It's going to create a point location that we are then going to use for sampling image collection. One thing I don't think we mentioned earlier is that whenever you put a line by itself, the notebook tries to display whatever the object is in there if it's not being assigned to something. So in this case, there's a stat region get info. And the get info is key because that says have Earth Engine backend run it and return the result. If you don't have that get info method in here, and I ran this, I'm going to get a definition of how do you calculate this stat region. It's like it's a geometry that is called by a function geometry constructor, which can get really verbose, especially if you have been building up basically a object, computing an object by combining a bunch of methods together. So right now, and this is something also that might change in the future with the Python library, you do have to put in the get info in order to request that information from the server, pull it back to the client. All right, so we have our point. We are going to take our with NDVI collection and filter it for that particular region. So we're going to reduce the number of images to just the ones that are at that point. And then I'm going to define a function that takes an image. In this case, I called it img as my variable. And then it runs this reduce region, which Kayla showed earlier. It's a spatial region that is defined by the stat region variable. And then it's going to take the mean value within that region. And then finally, it's going to run it at the value of 30 for a scale. And then the rest of the thing that this function does is it constructs a feature with that statistic. And then it sets the time of the feature based on what the time of the image was. So we're basically trying to keep track of when this image occurred, keep that as a variable in there, in addition to summarizing the region. And I keep saying region like this, but it's a point actually that we define. It's a geometry that we're summarizing. So I'll run that function, which just defines it. And then finally, there's a couple of helper functions that we need. One is to convert a Earth Engine feature collection into a dictionary, which is down here, and then finally another one that will take a feature collection and then convert it all the way over to a data frame, which first converts it to a dictionary and then a pandas data frame. Pandas is the kind of the standard Python geospatial data, or not geospatial, data science library. So data frames are a very kind of ubiquitous data structure in Python, and so that's why we want to get our feature collection data in there. So anyway, there's 3 helper functions here in a row. Let me just show what the result is once we run them. Oops, I commented out a little piece that actually shows the result. And going back to this code, we have a feature collection called filtered that was defined earlier on. It was when we took our original image collection, filtered it down to just where it's intersecting a point. We mapped the reduce region function over it. And then finally, we got rid of all the null values, because sometimes your point and your image might not necessarily perfectly intersect because the boundaries of the images are somewhat approximate. So sometimes you have to get rid of the null values there. We converted it to a data frame. We basically changed the timestamp in that data frame to be more of a Python-looking time. I'll have to scroll over to actually see the result of that. See, there's a timestamp here. So this was in 2013 that image was taken. But now we basically have all of this information back locally on our computer in a Python data frame, so then we can start using the rest of the Python ecosystem, visualization tools, et cetera, in order to manipulate that. And so what I am going to do is process that data frame in order to make it in a format that's appropriate for this Altair visualization library that we're going to use. And so that's what this code is there. It's just a little bit of manipulation of the different bands in the data frame. The end result of this is, did you want to say something?
Yeah,
Yep.
we also chose only a couple bands.
Yep.
Before we had a bunch of bands.
Yeah, so we selected down to just be a few bands here. I'm only showing band 5, but that's just because I'm taking the first 5 values of this longer data structure. And so we have basically a time, what band we were looking at, and what was the value of the band. And it's a very long data frame that has that type of information in there. And then Altair, which is the graphing library, can take that information and parse it out. So this code will take the data source that we just defined. It's going to mark it up as a line encoding the data in a certain way. It's going to use the timestamp for an X value, that value of the band Y, or value for the Y value, and then it's going to use band, which was another one of our columns there, as the color. So we will have 3 different bands, NDVI and the B5 and B4. And as I run this here, it basically creates this plot that once again encodes the bands here with the different colors. The timestamp is now the x-axis. The value of the band is on the y-axis. So Altair is this kind of, it's called a grammar of graphics type of mapping library, is that you construct a data set and then you map encodings of like what value or what parameter should be associated with different characteristics of the graph. It's a really incredible library. If you just Google for like Python Altair examples, you'll get hundreds of these different graphs that all have that sort of similar construction of taking a data source and encoding it in this way. Any questions on that whirlwind of how to get data out of Earth Engine into a data frame and then use something like Altair to make a graph out of it? So there are a lot more steps here than you would have in the code editor, but also a whole lot more flexibility of what you would do in terms of visualization.
So I just want to understand what I'm looking at here. So every point on the x-axis is one image, right? And it has a timestamp. And then every point on the y-axis is the the reduced, so the value at that point, right, for all these bands, NDVI, B4, and B5.
Yep.
And remind me, what are B4 and B5?
Those are the red and infrared channels that are used to calculate NDVI. So if I'll zoom in here a little bit, because it's an interactive graph, the NDVI value, which is this green one, is going to be the normalized difference of whatever these values were up there.
Okay, got it.
So it's showing how that varies over time. Well, sometimes we will do this where we'll point out how does a forest look different than an urban area, things like that. What might be a little bit confusing here is that it's showing them as lines even though they are discrete samples. But if you did something as simple as like do a point marker instead of a line encoding, then this is, well, maybe that's not easier to interpret, but basically that is showing, how it varies over time and exactly like when that point is representative of it.
You can also share, like, when I was first looking at different Python visualization libraries, Tyler pointed me to this talk from PyCon in 2017 called the Python Visualization Landscape Talk, and it goes over a bunch of different Python visualization libraries and like why you would use one over the other. So like if you're starting out and you're wondering what package to use, that talk could be a good first starting point.
Yep. Yeah, I would say that Altair is more targeted towards data exploration. There's a lot of other ones that are more towards making like a chart that is appropriate for putting into a publication. I mean, Altair does a lot of interactions and sorting and filtering for you. Other ones are more even fancier and like what the output looks like. Okay.
Exporting images.
Exporting images, our last
And this is our last
little section.
exercise.
Yep. Whoops. Oh yeah, I gotta go down to here. All right, gonna click down to exporting images. All right, our last one is just to show how to get one example of how to get your data out of Earth Engine. We are actually going to kick off a task that will do an export. So I'm going to go a little bit quickly through this first part because we've seen this already, at least the calculation of the greenest and how we can define these visualization libraries. One thing I will point out though is that this special star is how you can pass a Python dictionary and have it look like it's passing keywords to the visualized library. So that's something you won't see it in JavaScript, but it's something that can become very helpful in Python in order to define stuff in a dictionary, modify it in a dictionary, but then eventually pass it as keywords. All right, so we have this visualize command here is going to construct the visualization object, and that makes it basically is constructing a 3-band RGB visualization object. So it might have started off with a lot of bands like Landsat did, and then reduce it down to 3 that correspond to RGB. And after we got that run, we can add that to a map just to make sure this visualization looks like a RGB image. So I'll zoom out a little bit, and I mean, it sort of looks like a cleaned up satellite image that you have the Central Valley, very verdant area, and then this is getting out into Nevada. That's drier desert-like environment. So that looks good. So now let's export that visualization, and in order to do that, we will define where it's going to be stored. And so my account here has a folder called projects EEEE test TE. I don't know why I chose that when I was setting this up. But it has an assets folder, and within there I created a temporary folder so I could just export something from here. So all of that I did, I think I actually went into the code editor, set this up. You could do that programmatically within Python, but for now let's just assume that folder exists. And then we are going to define a task using the Earth Engine batch library. It has a different module in there called export image to asset. This corresponds to the same export image to asset that you see in the JavaScript code editor. There's a few parameters that we're going to pass in there. The image object that we want to export, a description of the export, where we want to export it to, and then a little bit of like what is the range for the image that we want to export, the region, and at what scale. So I could kick this off. Well, first I'm going to define the task. The next one that's commented out here starts the task. You don't need to do this, especially it's going to fail because it's going to say, hey, that data already exists eventually. But I just want to make sure that you know that you have to first define a task and then start it. This is equivalent in the code editor is you define a task and then you click on it. But it's a lot easier to kick off hundreds or thousands of tasks in Python using this approach. So that one did, well, we're going to go see how it's doing right now. It's actually still running. I think it will fail eventually because it's trying to overwrite something that's already there. But I just went into our task manager page, the same one that you can access from the code editor, to check on the status of that task. The last time I did this, I think it took, oh, there it is, took about 13 minutes to complete. That's going to vary depending on who's using the system. But eventually, you will have a way to instantiate an image object with that ID that you just exported, and that then can be displayed back on the map. So I exported a region of California and Nevada, well, I guess it's mostly in California, out here, and exported it, and now you can use it back in the notebook or in the code editor. You know, at this point, it's just a new asset that you have created. So either way. So that's just a very short example of doing this, but it's very useful to do it in Python because you can export hundreds or thousands of images, which is sometimes hard to do within the code editor without modifying the code editor in some way. Question?
Questions about, oh, thank you again. Two questions about the asset ID. One is, like in this example, at the tail end of the asset ID, the name of the asset is what's final. That's not like the name of the folder the asset's in.
That is correct. This is the name of the asset in there.
Okay.
Yeah. So
And
all the way up to there, it was basically the users folder and assets. So this is kind of all fixed. And then after that, you can add additional folders if you want. And finally, you end it with the name of the actual asset you want.
And then creating those folders, you would have to do, could you do that in a Colab notebook, or would you have to go into something else?
You can do that in a Colab notebook. I didn't show how to do this, but there are commands for making folders within there. It's actually in the same EE batch module, I believe, of there. But that would be a good example that I should put together.
Okay, thank you.
So I don't have to go back to it. Yes. Early on, when we were going through the auth flow, I did point out there is that checkbox for read-only auth. This will fail for that reason if you basically restricted it to be read-only. But if you're not actually going to be exporting things and you're using a library that somebody else provided to you, it's probably the safest to click that read-only scope.
Another thing that we didn't show, but it's good to keep in mind, is you can programmatically, using Python, cancel tasks. So like with the code editor, normally you have to go in and just manually click X a bunch of times.
We now have a shortcut now in the
Oh,
code
you
editor.
do?
That you can
Okay, never mind.
Cancel them all. But
I
that used to be a
I
problem.
didn't know that that was a shortcut.
Yeah.
It is nice to be able to cancel it here too.
Yep. All right. So that concludes our notebook examples. We do have a few more slides to go back to. And this is what I saved you from going through in the auth. So congratulations on going through authentication so fast. It saved us. All right. Just a few other things that I wanted to touch on. One is that we've been showing everything in Colab, which is really good for teaching because we can get people spun up fast. But if you're working on it for hours or days, it can get a little bit annoying to have to deal with recycled virtual machines, because if you stop using Colab, even walk away, get a cup of coffee, it might recycle it if you're gone for enough time. So An alternative to that is using an environment that basically is persistent for you. And one option is using Jupyter Lab, which is the implementation that is created by the Jupyter project for displaying. It's basically a workspace for working with multiple notebooks at the same time and other types of data. And that can be installed locally, or it can be installed in a cloud environment. And you will have to pay for the cloud resources if you install it in a cloud environment. But it allows you to keep your credentials for days or weeks or however long that you actually want that environment to be stood up, or locally. And I do this most of the time when I do Python development. I'm actually using Jupyter Lab stored locally on my machine or installed locally on my machine, just because I work over the course of days on the same thing. So if it's still running here, I'm going to go try to find where I had that. I think it was my other window. Oh, maybe I recycled it there. All right, let me go. There we go. All right, so this is going to be just a quick showing what it looks like to have it running locally. First, I stopped the Jupyter Lab server that had been running on my machine. Don't worry about trying to read this at all. It's basically an invocation to start up the server on my local machine that will bring up Jupyter Lab. And now I have an environment that I can use that uses my local credentials that I've stored to my hard drive. And it can have multiple panes of designing code, copying code between different notebooks, etc. A terminal shell at the bottom, a file browser. It's a more complex, full-featured environment for working with these Jupyter notebooks, in short. And it has a different set of menu items than you would have if you were in Colab. But they all are sort of similar, like running cells, running all the cells, et cetera. But this is what Jupyter Lab can look like. Somebody had asked about Git integration, and it even has a tab that's over there on the side that I just loaded up that's going to show which of my notebooks has changed relative to the last time I saved it to version control. So a lot of more advanced development functionality within an environment like this. It's not the easiest to teach with because it's a lot more complex, but I did want to make you guys aware that this exists. And when people are doing a lot of Python development, they will usually move from a single pane notebook that is available like Colab to something more full-featured like this. All right, back to our, and this is just a table of kind of the different pros and cons of each of them. I use them both. They're both very useful, but just for different purposes. And then I do want to point out that the map functionality that we were showing today hasn't existed very long, at least that library hasn't existed very long. It's in a Python library that I just published a couple of weeks ago called Earth Engine-Jupyter. It's available on GitHub. That is the source of truth. You can submit issues to it if there's new things that you would want the library to do. I'm going to try to keep it pretty low level in terms of like making these building blocks of like map inspector, maybe a task explorer, things like that. Because there are others in the Python community that have already built these amazing libraries on top of Earth Engine. I just want to give them a more stable surface to build those libraries on top of. GEE map by Qiuxing Wu is a really good example of that. Has a tremendous amount of functionality that works in a notebook and in other environments. But we are trying to make it so that some of the low-level code doesn't have to be repeated across all of these different Python libraries that people are building on top of Earth Engine. So if you're interested in that, I'd encourage you to just check out the GitHub repo, talk to me while you're at the conference, give me ideas of like what you think would be important to be in a library like this. And let's see what else we have here. Oh, and then our final thing, that slide that we had is if you liked what you saw here, you think you're going to use more Python, Earth Engine in your world, there's a few other presentations that I'd like to point you to that will be using Python to some degree. One is Kel's talk tomorrow over here, this capacity building. And this other one on day one, unfortunately, it was going on at the same time, so you'll have to watch the recording of that. But the one that was talking about TensorFlow is using a lot of Colab notebooks. That is what I remember. Is there anything else that we needed to say at the end?
I don't think so. Do you guys have any other questions?
And it doesn't have to be questions about what we presented either. It's just like, I want to know ideas for the future of like, where should we go with this type of development for Python users?
Well, first, just to say thank you both for a wonderful presentation. What if you develop your ideas in one of these notebook frameworks, but then you want to be able to address your code through the command line kind of functionality? How would you transition that?
That is what I've been doing in the development of that library, or I've been addressing that issue. I'm going to point you to a new library that I have been using to develop code called NBDev, which you start in the notebook, but it creates these modules on GitHub. The Python package that I created was using this NBDev because these notebooks in general are very good for experimentation, but not everybody wants to work in a notebook. There's a really famous talk that was given at JupyterCon at one point of like why I hate notebooks. It's really entertaining. I encourage you to watch it because they do have a lot of characteristics that freak out kind of professional software developers. NBDev has found a really good, I think, middle ground of like showing how they can be really useful for producing a lot of the artifacts that you would do outside of a notebook normally. But yeah, you can use notebooks to create artifacts that work outside of notebooks. Yep.
So this part about using Jupyter Lab and saving the credentials to be able to have longer, persistence seems very interesting. Is there an example of how to do that somewhere?
When you run EE Authenticate, it will store it on whatever server is local. So if you're running it on your own machine, it's going to store it in your home folder .config/earthengine/credentials, I believe. It does the same thing in Colab. It's just that server gets recycled. So it's sort of the same regardless of where you're trying to, yeah. I guess it's not really a mystery too much about like where it saves it. It's just whether your environment disappears or not.
Yes. So if you would work with these tools on city and urban environments, are any good places to go, sort of where you can start with building heights and building characteristics and city characteristics, and libraries that would help you applying satellite data to that environment and not on greenery and
yeah. So there is, I guess, relatively little high-resolution geospatial data that we have available in the Earth Engine data catalog that would apply to the detail of cities. For certain countries, there are some extremely high-resolution DEMs where you can start to get an idea of what the footprints are. I know the Netherlands released a really detailed DEM. I think one of our Earth Engine developer experts put in a high-resolution map of France recently. But other than that, I think you're mostly having to find the data sets and upload them yourself into Earth Engine. We've been focusing more on like globally consistent data layers. And so something that was really detailed for individual cities won't be so much in the catalog. There are some people that are here at the conference that are working on kind of urban-related issues that might be interested to talk to. So I would suggest that you look through the bio slides of the conference attendees. Have you seen that notebook that Raleigh had shared of like the attendees can share what they're working on? I think there are some that are in there. Talk to me afterwards and we could put it out. Yep. Yep, so there are, that is correct, for large If you're looking at distributions over like a large region, there are some Landscan, WorldPop. There's these population data sets that are available in the Earth Engine catalog. But maybe I misunderstood a little bit. I thought you were working on very specifically within a city. Yep. So I think you, for the most part, you will have to find the data and upload it yourself to there, but be interested to learn exactly which data sets that would be useful. And maybe we can find a source that would work for you.
I have two very dumb questions. Are you ready?
There's no dumb question.
Oh no, this is a pretty good one.
Really?
You
No.
showed us how to save an image to our drive,
Yeah.
which is great. Is that image like an image object or a geotiff or?
It
That's part
depends
one.
on how you exported it. By default, if you're exporting an image to drive, it is going to be a geotiff, yes.
Love that. Awesome. Second dumb question.
I think actually what I was showing in there was exporting to a asset in a folder that you could, I didn't actually get it all the way out to drive, but there is an option to export to drive, and then you will get a geotiff.
Super. And inevitably, after many hours of searching, documentation checking, serious examination, is there someone we could reach out to if we are incredibly stuck?
There is a large, vibrant Earth Engine community that will accept questions. As I said earlier, it is harder to ask a question that is reproducible when you're working in a Python environment. One way you can do is code up a really small example in a Colab notebook and then share it publicly. And that's something that you could link to from within the Earth Engine community forums. But there's a relatively, I guess I would say that there are fewer users that actually use Python of Earth Engine, but when they use it really extensively. Like probably half of our use of Earth Engine is through the Python API, just because they use it very heavily when they do. So that's probably not a great satisfactory question to where.
But it's an answer, and I'll
Yep.
take it.
All right.
So like tags in the Stack Exchange for Python?
Yeah, in GIS Stack Exchange, which Kayla brought up here, there's a few different tags that are in there. One is for Google Earth Engine. I'd have to find it.
Yeah, right
Google
here.
Earth Engine. There's also Google Earth Engine Python in there. So that's another place that you can ask Python specific questions. It might get some attention.
You could also talk,
Oh, sorry.
I was just gonna say like this to asset, it's probably, like for your drive example, I think it's probably to drive.
Yep.
Suppose you've got a big library of JavaScript functions and things like that, or vice versa, you've got a big library of Python functions. What's your kind of workflow to translate from one to the other?
Unfortunately, my workflow usually is manual, converting back and forth between the two. There are some libraries that people have written to kind of do a first pass at a translation. If you look at Qxing's GEE map, I think that there is a function in there that tries to do that conversion for you. And it gets you most of the way there. You might just have to clean up some of it. We have experimented, and we discussed this a lot on the team of like, how can we save it in a language agnostic form so that others might be able to call it from a different client library, and we don't have a great solution for that yet, although we've been thinking about that for years. So unfortunately, right now it still is quite a bit of manual work to convert one to another. Yep. Oh.
So suppose that instead of using a notebook, you want to write actually a web server in which you want to do your computation in Python, accessing some of data here and there, and also the Google Earth Engine data. But then you want to send some map object to the UI that is able to do the visualization. Is this doable, or should I really be looking at JavaScript Earth Engine API then?
It is doable. It is a lot of manual construction yourself to use it within a Python web framework, the library. Well, that part's not too bad. But then whatever visualizations that you have, you're going to you'll have to get ones that don't necessarily rely on the notebook itself. But there are other Python visualization libraries that work outside of the notebook that you could use for that. A lot of the websites that we see accessing Earth Engine that are designed by a full team of like web developers will do exactly that. I mean, because they have the skills and they use the flexibility of web development to call Earth Engine either from the JavaScript or the Python library and then use all of the different tools for displaying maps and charts on the screen. So I'd be happy to show you a few examples of those or point you to them if you needed. But it's definitely possible, but it does require some specialized web development skills in order to pull that off generally. We have some trivial examples in the documentation of how to do that. But any last questions? We are at time, but all right. I'd like to thank you all for attending our session. Hope you learned a lot.